Hi everyone, welcome to the Research for Industry talk today. I'm Connor Kelly, a project manager in the Azure Global Energy team focused on environmental sustainability software engagements with our customers in the energy industry. Before I introduce the speakers, I'd just like to point out the Q&A. So if you have any questions during the talk, just go right ahead and put them into the tool. And after the talk, we'll start running through those in a live Q&A session. So next I'll introduce the two speakers today. So the talk is Out of Thin Air, which is focused on direct air capture. We're privileged to be joined by Professor Matthew Realff and Professor Christopher Jones. So Professor Realff works on the areas of energy and sustainability, complex systems and biotechnology. And so both are out of Georgia Tech. And Professor Christopher Jones is a professor of chemical and biomolecular engineering at Georgia Tech, directing research programs focused on catalysts and CO2 separation, sequestration, and utilization. Both have very extensive publishings and research programs. So we're really glad to have you here today. And I'd just like to introduce you and ask you to go ahead with the talk. So thank you very much, and over to you.
Thank you for that introduction, Connor. So the talk today is Out of Thin Air, direct air capture of carbon dioxide to walk our carbon footprint backwards. And I'm delighted to be here with my colleague, Chris Jones. So as we get going, I would like to start with our main messages of this talk, just in case any of you don't get the opportunity to join us for the entire time. The first of those is that we typically, as scientists and engineers, solve problems and create new ones in the process. So the most classic example of this in the chemical engineering field is the fact that before the invention of the Haber-Bosch process, which fixes nitrogen from the atmosphere, we would have regular and repeated global famines. But with the ability to create fertilizers from nitrogen fixed from the air, we have essentially solved that problem, which led, of course, to an explosion in population. And as a result of an increase in population, substantial increase in energy use. Second is that history shows that we can respond in rapid and focused ways when we resource the science and engineering to do so. And here are three examples of this. Obviously, the Manhattan Project in the 1940s, the moonshot in the 1960s, and the Human Genome Project in the 1990s. Climate change is the defining challenge of our current era. If we don't solve this, people will look back on this and hopefully reflect on what contributions we didn't or did make to this problem. We need to solve this problem, and we need to solve it now. In fact, today there was a report by the UNEEP on the emissions gap, which would demonstrate that the national climate pledges that have been made to this point would lead to global warming in the 2.7 degrees C by 2100. So this is a very pressing problem. Negative emissions technologies, which are ways of pulling CO2 out of the air so that we can reduce the concentration of CO2, along with renewable energy, are the answer to solving the problem of climate change. In other words, we have to be able to walk our carbon footprint backwards. And in this point, I would say there is all of the above. No one technology is going to solve this problem. We're going to need a variety, and one of those will be direct air capture. Direct air capture is a technological approach to removing CO2 from the air, and it's a very scalable negative emission technology. And that's really what we're going to focus on today in this talk, is really to explain how we can achieve direct air capture, why it's feasible, and the outlines of technologies to do so. So direct air capture is today's Manhattan Project, or moonshot. So I'm sure we're all familiar with this Keeling curve that shows the increase in CO2 from 1960 here to the present day. And if we look at today's concentration, or the average of last month, it was 413 parts per million. A substantial, maybe 150 ppm increase above in pre-industrial levels. Now, if we were to make an estimate of what we might be able to achieve with renewable energy, Our current emissions today are about 40 gigatons of carbon dioxide per year. And if we were able to hold that steady through 2040, which with growing population and growing GDP is quite challenging in and of itself, and then we were able to ramp that down to maybe a residual level of 10 gigatons per year by 2070. This is probably one of the most ambitious of the emissions targets that we have on the table today. What would happen to our atmospheric CO2 is it would rise from its current level of roughly 413 all the way up to 520 parts per million. And that was one of the reasons I mentioned that our current pledges, which would lead to emissions profiles that would not actually match this but be higher, would lead to global warming in the 2.7 degree range, which is significantly above the targets of 1.5 and 2 as a more modest target. So how do we walk our footprint backwards? If we end up having a lot of CO2 in the atmosphere, we're going to have negative emissions technologies, even if we're able to achieve fully 100% carbon or fossil-free energy. We still will need to bring this concentration back down. So I like to think of this as the problem of stopping the flow and draining the tub. So I live in a Victorian house, and I actually have one of these clawfoot tubs. And what we have to do is we have to work on capturing CO2 from point sources. But if we do so, we only change the rate of accumulation. We only change how fast the water is accumulating in the bathtub. And if we accumulate too much, we're definitely going to need negative emissions technologies, which will remove CO2 from the atmosphere. And this was outlined in a report from the National Academy of Sciences and Engineering, where they looked at the negative emissions technologies and reliable sequestration. And they did so across a variety of different technologies, examining each of their scales. And actually, Professor Chris Jones was one of the major authors on this study, where he examined the topic of direct air capture, along with other authors who examined things like mineralization of CO2, the enhancement of systems in the ocean, the enhancement of afforestation, and changes in agricultural practices. If we take a look at sort of the emissions profiles that we've seen to this point, what we would see is again, this idea that maybe we could hold it flat and then bring it down, or maybe if we went as business as usual, we would have an even greater increase in our CO2. And that to essentially avoid having a large residual amount of CO2, what we need to develop is a negative emissions technology that will bring down the emissions from their residual level and actually potentially create net negative emissions by the end of the century. So we're going to do this through the conventional renewable energy use. We'll do it by reducing the amount of emissions, and then we will add our carbon removal technologies. But the "and then we will add" does not mean that we should not start on these technologies now. If we had these technologies in place, we would be able to potentially avoid some of the negative potential consequences of having high CO2 levels in the middle of the century. So the estimates provided in the National Academy's report talk about having 10 gigatons per year removal by mid-century, requiring 20 gigatons per year removal by the end of the century. Now, if we think of this in terms of the industry that this would support, this is 25% of the 2020 fossil fuel industry in 30 to 40 years, and 50% of its size in 75 years. So basically, we're talking about creating a new industry that is of comparable size to our existing fossil fuel industry. So that's a very significant opportunity for technological innovation. So as I say, let's look at the various different opportunities. One is coastal blue carbon. This has got low cost, but ultimately the amount of shoreline that is suitable and the amount of biomass we can accumulate on that shoreline is relatively limited. On land, we have the idea of afforestation, which is relatively cheap, and soil carbon enhancement, which is also relatively cheap and can be scaled up to moderate levels. We can also think of a combination of natural and technological systems, such as biomass energy with carbon capture or storage, which is referred to as BECCS. Now, this particular technology, again, is going to use the biomass, produce some energy from it, and then sequester the CO2, both in the form of putting it into rock formations, and also possibly by creating a biochar that is used again for soil enhancement. The focus of our talk today will be direct air capture, which removes CO2 from the atmosphere using technological systems, and again puts it down for sequestration. The last remaining technology is the idea of accelerating the weathering of rocks by essentially creating greater surface area. And this technology is very nascent. We don't really know how this will actually end up unfolding, but does have significant potential if it were to work out that it actually can sustain the rates of capture that people would like it to if we grind the rocks up fine enough. So where have we come with direct air capture to this point? So really the original use of direct air capture technologies was for spacecrafts and submarines, where you have enclosed environments where the CO2 will simply build up if you don't remove it from the atmosphere. When we remember the Apollo 13 mission and maybe the film, where that in fact is assembled by the team in flight based on designs developed on the fly at NASA. In 1999, one of the pioneers in this field, Klaus Lackner, proposed that large-scale direct air capture was feasible as a climate mitigation strategy. And really, since that time point, it's really sort of bubbled around in the background and now eventually is starting to come forward as a possible technology. So in 2008 to 2010, we had the first demonstrations and formation of companies of what is called temperature vacuum swing adsorption processes. And we'll come back to describe those in more detail as the talk unfolds. And really, there are three leading companies in this space: Carbon Engineering, Global Thermostat, and Climeworks, which is a European company which has engaged with Microsoft, or Microsoft has engaged with them to actually buy some of the outputs of their direct air capture plants. In 2008, 2009, Global Thermostat and Georgia Tech married the technology that Global Thermostat was developing from a process perspective and the sorbent technology that Chris Jones had actually developed here. In 2011, there were the first sort of reviews of the direct air capture approach, and this 2011 American Physical Society report was hugely influential. Basically, it claimed that direct air capture of CO2 with amine sorbents using the conventional technology was about $1,000 a ton. And unfortunately, this report received a lot of press, and actually a lot of people felt that this meant that the only way we were going to do direct air capture was to have costs of roughly that level. But of course, in fact, if you think about inventing technologies that are different from the conventional technology, there are ways to bring this cost down, and that's something that we'll talk about as we go through this. And in 2016, this comprehensive review of DAC materials was published, and this has a very, very wide set of materials that actually are being used or have been used or explored for direct air capture. So why is direct air capture possible? So I'd like to take a moment to sort of talk about thermodynamics. Thermodynamics is possibly the foundational topic area that we need to be able to understand this. And what it turns out is that if we have a feed which has a certain concentration of CO2 in it, such as the 400 parts per million in the air, or the 14% in, or 10 to 14% in flue gases, we can actually work out how much energy it takes to unmix a certain fraction of that, the CO2, with a certain purity and reject the raffinate or remaining stream. If we look at this, we actually find that this energy scales not with the concentration, which is a factor of 1,000, but really actually scales logarithmically, so that the amount of work required per mole of CO2 is only 20 kilojoules relative to 10 kilojoules for post-combustion capture. So this gives us the possibility that, in fact, if we only double this, that it means that we really essentially can solve this problem at this level, and we don't have to rely on trying to do it from post-combustion capture only. And this is a very significant fact in the overall system analysis and design. So if we have a dilute input stream and we want to design a separation process to produce a concentrated product, what is really the basic outline of what that process needs to do? And the question we have to ask is, where do we apply the work in this case? So if we require to apply the work on the dilute input stream, what will happen is we'll spend a lot of effort here, and that will be extremely expensive and extremely energy intensive. However, if we can apply the minimum amount of work here, such as, for example, pushing the air, and actually have a spontaneous process, which is exothermic, that captures the CO2, and then we put the work in on the desorption or removal of that CO2 from the material, then we essentially concentrate our work on a much smaller amount of mass than if we do it to the dilute input stream. And this is really the difference between something like a direct air capture process and a mining process. In mining, you have to put the work in on the dilute input stream to remove the ore from the ground, crush it up, grind it, to be able to get to the gold. But in the case of direct air capture, we can just move the air through a contactor, and that can be our driving force to then essentially remove the CO2 and then apply the work on the other side. So do as little work as possible on the feed stream, i.e. move the fluid, which we know as air is relatively lacking in density and moves fairly easily. We have windmills. Windmills, in fact, are roughly the same size as you need for a direct air capture system, although often implemented with smaller spinning fans. Use the spontaneous exothermic process to adsorb it, and then apply the work or heat to remove the CO2 to produce the concentrated product. So with this as a rough outline of what we need to do, I'm now going to move into just describing the essential components of a direct air capture system before I turn it over to my colleague Chris Jones to talk about more of the details. So the first thing that we need is we need a material that will actually capture the CO2. So basically what that comes down to is something that at 400 parts per million CO2 in the gas stream will actually enable a certain amount of CO2 to be removed. And then we must be able to vary the temperature or some other property to essentially allow that CO2 to be removed from that material at a different condition. So that's the fundamental thing we have to have, is a material with a high capacity for CO2 at low concentrations. The second thing that we need to do is we need to avoid this high amount of work going in on the front end. So what we need is we need something that has a very low pressure drop so that we don't have to put a lot of energy into the air to move it through the contactor. And so that leads to the idea of having structured contactors with large porosity to allow the air to flow through them with low pressure drop. But we also need to have contactors that have large surface area so that we can present this material to this CO2 so that it can be captured. And we've basically explored here monolith structures and hollow fibers, and we'll come back to what those are later. And then lastly, we have to design a cycle that will go between this adsorption and desorption to be able to apply this contactor to capture CO2. And what we want to do is we want to have efficient adsorption for long time periods and then relatively fast desorption so that we can then send our material back into our adsorption. This will allow us to keep the productivity of tons of CO2 per meters cubed of structured contactor per hour as high as possible. Okay, with that, I'll turn over to my colleague, Chris Jones.
All right, thank you, Matthew. So with that outline that you gave for what a typical process will look like, I want to walk through 5 individual elements that I believe are the key elements that have to be put in place to achieve a practical DAC unit, essentially recapping one slide for each of the key topics you introduced on the previous slide. So here, talking about designing a material that is selective to the very dilute CO2 in the air versus nitrogen, oxygen, and water and all the other species that are there. We can imagine doing that by designing a binding site that wants to selectively grab that CO2. And the amine site shown in the center of the slide here is one where the chemistry for binding with CO2 is outstanding, and it leads to very, very high selectivities and large uptakes as manifested in the adsorption isotherm on the left-hand side. So on the left-hand side with this adsorption isotherm, the amount adsorbed on the y-axis versus the concentration on the x-axis. And what we see is that the isotherm shown in black for the chemisorbing amine material gives a very, very high capacity, even at these low partial pressures that are corresponding to 400 parts per million CO2. In contrast, the conventional sorbents that have been used for a long time to capture CO2, something like zeolite 13X with the red isotherm, which is a physisorbent, works very well at high concentrations, and in fact is the basis for industrial gas separation processes today, but is not very efficient at the low concentrations necessary for direct air capture. So one of the first and counterintuitive desires for this type of ultra-dilute separation compared to existing gas separations is to use a chemisorbent with a strong binding energy that gives you that high selectivity at low partial pressures. Next slide. So we'd like to then take that sorbent and coat it onto a structured contactor like you introduced previously, so that you could get very high gas throughput with very, very low energy expenditure. And we're going to talk about that energy expenditure in the context of what we refer to as pressure drop in chemical engineering. And if you can minimize the pressure drop required for flowing gas, you can minimize the amount of energy you have to put into the system. So these low pressure drop, high surface area contactors are ubiquitous today in the world. And anyone who has a gasoline or diesel powered car owns one of these, because these are the contactors that exist in the catalytic converters of our cars. And in our cars, they're coated with precious metal catalysts that clean up the exhaust coming out of our cars and remove hydrocarbons and carbon monoxide. What we would do for direct air capture is coat these with the type of amine materials or another suitable material that I showed on the previous slide. And then we can get very, very high gas velocities with very, very low pressure drops. So we can get pressure drops on the order of 0.02 pounds per square inch, even with the gas velocity of 5 meters per second, which is the wind velocity that you would experience on a stormy, windy day outdoors. Minimizing this pressure drop is important because based on a techno-economic analysis for a DAC process that Matthew and some other colleagues did earlier, if not properly designed, the cost for moving that air around can be as high as 30 or 40%, but with a properly engineered system with low pressure drop, you can reduce the cost of moving the air down to the order of 10 or 15%, as shown on the right. So next slide, please. So I said that we had to have a sorbent that captures a lot of CO2, and that's a representation of adsorption thermodynamics. We also want to be able to remove that CO2 after we've captured it as quickly as possible. So we'd like to adsorb and desorb very quickly, recognizing that this process is cyclical, alternating between adsorption of CO2 and then collection and desorption of CO2. And we can achieve that using these adsorbents on a monolithic contactor, as shown on the bottom right-hand side. And what we would typically do, referring to the plot on the left-hand side, which shows the total capacity normalized to 1 at the maximum as a function of time, we wouldn't wait to completely fill the entire monolith. Rather, we would stop early in the process at the blue line, where you're exiting the linear regime, where you could get 80% of the total achievable capacity in a reasonably short time. And we show you here on the laboratory scale equipment, that short time is on the order of 100 minutes. That's relatively long for an adsorption cycle, and that's why we need to move out of a laboratory scale contactor and into a contactor like the monolith shown on the right-hand side that's designed to give us very, very high gas velocities on the order of 5 meters per second. And if we do that, we can shorten that cycle time from about 100 minutes down to about 15 minutes. So getting a lot of air through the system is very important because as a figure of merit, if we consider the desire to remove 1 ton of CO2, and if we're going to remove 70% of the CO2 that passes through our process, we have to process 3,500 tons of air to get that 1 ton of CO2, owing to the ultra dilute nature of air. And this is why fast gas throughput through our process is critically important. Next slide, please. So as Professor Realff indicated, we essentially in some ways get the adsorption of the CO2 on the sorbent for free. We design a selective sorbent shown in yellow that can selectively bind CO2 shown in red. And so it'll pass through, and as soon as it hits the surface, it'll stick to the surface. And that happens spontaneously as long as we're efficiently moving the air through the process. But we do have to put energy into desorbing and collecting that CO2. That is the endothermic step. The nice thing about a lot of the sorbents we have studied at Georgia Tech is they only require low temperature heat on the order of 60 to 120 degrees C, which is considered waste heat and is available in some manufacturing processes, for example. So we can imagine bringing that heat in the system to liberate the CO2 from those yellow adsorbent spheres. Next slide, Matthew. By bringing in steam, And the steam then would contact the sorbent and break the bonds between the CO2 and the sorbent, producing a mixture of now, instead of CO2 and air, now CO2 and steam. And if we cool that steam, we can then drop out that liquid water, as shown in blue, giving us a nearly pure CO2 stream in red that we can then use for sequestration or other uses. And so we do have to put energy in to desorb. This is where it's going to cost us some money. And we want to design our process to minimize the amount of steam that we're going to use in this step. Next slide, please. And so we at Georgia Tech have been working for the past 10 years with a startup company. There's about 6 to 12 startup companies in the world now that I'm aware of that are looking at CO2 removal from air. Working with Global Thermostat, then we have built several generations of pilot or commercial scale equipment. One generation shown on the left is from early 2011, 2012 in Menlo Park, California. Another one shown on the right is circa 2018 in Huntsville, Alabama. And so Global Thermostat, this technology startup, used to have their R&D labs in Atlanta, co-located with us at Georgia Tech. And the company's grown so quickly recently, they've relocated to their own facilities in Brighton, Colorado. And I'll point out that I have done research with Global Thermostat for a long time and have a small financial interest in the company. And for that reason, I'm required to share the conflict of interest statement at the bottom of this slide. Next slide, please. So if we consider putting these 4 steps together now in that process that has many individual steps, the steps can be boiled down to 2 main steps on the left-hand side, an adsorption step and a desorption step. So that's 1 and 4 that he's pointing at now. And in between, we have some steps whereby we would evacuate the sorbent chamber, bring the sorbent chamber to pressure, we would desorb, and then finally cool the system after we've heated it up so that we can repeat that cycle. And we've modeled the techno-economics of this type of process using a combination of experimental data as well as process models. And we did it for a particular adsorbent, a metal organic framework film supported on a monolith contactor. We took experimental isotherms for adsorption measured in my laboratory and used that to parameterize the model. And then studied this removal of CO2 from 400 ppm air at 25% relative humidity using a 40-minute cycle time. And we calculate an energy of separation for what is effectively an nth plant, so a mature plant that has moved significantly down the learning curve, as having on the order of 0.15 megajoules per mole of CO2 of energy use. This type of process, if we compare it to a point source capture, so a flue gas capture where you're turning off the faucet in that tub rather than removing CO2 from the tub, we see that the total energy is only 1 to 3 times higher than it is for that higher concentration post-combustion solvent separation. And so while it's 400 times more dilute in CO2 concentration, the energy penalty, the excess energy penalty is actually quite small. And that's one of the reasons why we believe that low-cost direct air capture will be possible in the future. Next slide. So we had these 5 elements that I think are required for a practical process. And every single one of these elements has been demonstrated on a laboratory scale by multiple different groups around the world at this point in time. And what really needs to happen now is that these 5 elements need to be put together in practical processes that then get deployed and operated at scale such that we can learn how to operate the processes more efficiently and effectively move down the learning curve. So if we think back to solar energy in the 1980s, it was very, very expensive. But then through deployments and learning, altering the technology, deploying and learning, altering the technology, etc., we've moved down the learning curve to where solar energy is very cheap in many regions around the world today. And we can imagine a future for direct air capture that's quite similar. Next slide. So 2 questions that I get quite often when I talk about this, I'll just answer right now. One is with regard to land area. So can we actually do enough air capture to make a dent with the amount of space that we have on Earth? Because we've heard about land limitations for other types of energy technologies in the past. And so if we do a thought experiment and we take that mid-century negative emission target of 10 gigatons per year, And we asked the question, what if we were to do all of that doing direct air capture? Well, we don't think we want to do that. We want to do it with the whole suite of techniques, but just for the thought experiment, if we did it all with direct air capture, using numbers from the startup companies that are out there, how much land do the startup companies think would need to be devoted to get that 10 gigatons per year? And the calculation works out to be about 150,000 square kilometers, which is roughly the size of the state of Georgia. So I'm not arguing that we should take the state of Georgia or any state and turn it into a DAC deployment zone. But what I will argue is that amount of land somewhere on Earth, whether it be in 5 locations or 5,000 locations, is not a showstopper. We definitely have that amount of underutilized land around Earth. We could also imagine doing this on oil platforms and other locations, actually in the sea. And so we definitely have enough space, enough land to deploy this technology. Second question that I commonly get is, why don't we use natural systems like trees? Well, one answer to that is that as a species, human beings have not demonstrated yet the ability to reforest. We've only demonstrated that we can deforest on a global scale. So until we can reforest on a global scale, this will play a small part in the equation. We would like to do as much of it as we can because it's natural and low cost. However, even if we were to ask, if we were to ask the question, how does a DAC technology compare to a tree? Is a tree much better, much worse? So Matthew did a nice calculation using literature data, looking at a tree at the equator and how much CO2 it removes as a function of the ground area that it occupies. And he gets a number on the order of 20 micromoles per second per meter squared ground area. And your typical DAC process, if you do the same calculation, has a 25 times higher flux of CO2. So if we design these mini chemical plants that take CO2 out of the air, we can do it more efficiently than a tree at the equator, which means that it's a reasonable amount of efficiency using that as a benchmark. Next slide. So Matthew, turning back over to you, and then we'll do Q&A at the end.
Thank you, Chris. Just to talk a little bit about what we're doing here at Georgia Tech. As Chris has alluded to, we have been involved in DAC technology and materials since about 2008. We have a large collection of faculty at Georgia Tech who work in the area of gas separations and particularly even in the area of CO2 separations. And we've recently established the DIRAC Center, which is a direct air capture center that is looking at essentially across the broad range of topics that are of interest or connect to direct air capture. And we have a strong infrastructure and history of academic industrial partnerships in this area. And I just want to highlight some of those aspects. So the first question, of course, is why call it DIRAC? Well, Paul Dirac, a very famous 20th century chemist and physicist, actually articulated the thermodynamics of dilute mixture separation. And that is, of course, the inspiration for why we think direct air capture is a potential technology that can play a role in climate change, is because, in fact, dilute mixture separation theory points out that we only need a relatively modest increase in energy to separate a dilute mixture compared to a concentrated one. So that's one of the reasons why we decided the center should have the name DIRAC. If we look across who is in the center, essentially it's a multidisciplinary center that consists of folks like Chris Jones, who work on materials design and fundamentals, along with David Scholl and Ryan Lively. We have folks in physics and mechanical engineering who work on the fundamentals of contactor design. And then there's myself, along with my colleagues in process systems engineering, Fanny Bukavala and Joe Scott, who work in the area of process design and control. And then we've also got an active set of individuals looking at utilization. For example, Yongshen Chen in civil engineering is looking at coupling direct air capture with CO2 conversion using algae. And then in the area of sequestration, and in particular the seismic monitoring of sequestration, we have Fritz Herman. And then in the policy and life cycle analysis assessment area, we have 3 individuals working at looking at how to translate these technological advances into looking at how that should impact policy, and also to look at some of the broader issues around life cycle assessment. Now, I'd love to talk a little bit about the work in seismic monitoring of sequestration, as that connects directly with some of the topic areas that Microsoft has as a company. So what do we need for low-cost seismic monitoring to make sure that our CO2 stays in the ground where we put it? And what we really need is we need some open, transparent system that can enable us to lower the risk to society. And those risks come both in terms of where we should locate it to start with, and then making sure once we've put the CO2 in the ground that it stays there. So basically, seismic monitoring technology can mitigate hazards and account for the mass of injected CO2 so that not only can we make sure it's there safely, but we can make sure we know exactly how much we put there. So the approach here is to create an open platform, and it's modeled after the OpenAI type of architecture. And what we want to do is use this open platform to lower the cost of development to deploy this monitoring system, avoid the replication by multiple governments and multiple agencies to come up with this monitoring capability so that they can simply reuse the capability that's been created, and accelerate the innovation around this by creating the access to the code, data, and high-performance computing. Now, the type of questions we want to answer are, how often do we need to monitor by shooting seismic images to figure out how the long-term risks can be mitigated, and when we can, and how can we adapt as the sequestration project matures? In other words, how often do we need to do this? Can we in fact lower the rate once we've established how well the system is sealed? And what is the seismic detectability of CO2 plumes? Can we actually observe movement of CO2 in the rocks should we need to? So, for example, the density of the sites where we have to take the seismic measurements, and also how much we have to replicate the surveys to be sure that we have a real effect. And then what are the scenarios under which we can feasibly acquire the information? So to outline this in a bit more detail, what we start with is a seismic model which represents the rock in terms of the wave speed and the density of the wave speed of the seismic measurement and the density of the rock. And then we have to convert those measurements into the porosity and permeability of the rock to be able to understand, for example, how CO2 will move inside this particular set of rock formations. And what we do then is a flow dynamics simulation based on the permeability and porosity of the rocks. And here you can see a situation where CO2 in this area here actually finds a way to break through a crack or a fissure in the system and actually release into the upper rock layer. And so the question is could we monitor and detect this type of behavior in this system? So what we can do then is take the flows and convert those back to the changes in the rock and actually be able to figure out using a seismic model how that would evolve. And then we can take seismic measurements to essentially recalibrate to go back from our flow fields back to the density and wave speed of the system by essentially creating time analyses of the rock by seismic measurement. And that seismic measurement can then reveal not only the structure of the system, but also what are the changes that have occurred. And you can see here that this is a situation where the change is detectable through these seismic measurements. And so this enables us then to build this open platform of seismic monitoring that enables us to de-risk the sequestration of CO2 as we move forward. And this is the type of activity that the DIRAC Center wants to support so that we can actually complete the supply chain from materials development and process development through to the monitoring of the sequestered CO2. So here are the key messages again. I hope you have absorbed or had the opportunity to absorb some of them. History shows that we can respond in rapid, focused ways, and we believe that direct air capture is the next one in this line of projects that we've undertaken as humanity. And we believe that we need to undertake this because it's the defining challenge of our current era, and we have to tackle it, or we may well end up in a situation that is irretrievable with respect to some aspects of society. We believe that negative emissions technology, along with renewable energy, are the answer, but we need all of the above. We need a variety of these scalable negative emissions technologies, but the direct air capture will play a substantial role in this. And I hope that the last thing that we've managed to do is to convince you that amine sorbents supported on these types of structured contactors offer a practical, scalable approach to DAC, so as long as sorbent lifetimes are sufficiently robust. Now back to Chris.
All right, so we'll finish here. And if you're interested in this area and it's a new area to you, I want to encourage you to consider attending this conference on the fundamentals of adsorption in Broomfield, Colorado next May. This is the largest adsorption separations conference that occurs on a 3-year cycle. And a major emphasis this year will be on CO2 removal from point sources as well as from the air. And given that several of the startup companies in this space are also located in Colorado, we anticipate opportunities to see direct air capture facilities as part of this conference. So with that, we're very happy to have the opportunity to share what's going on in this space globally as well as at Georgia Tech. And at this point, I think we're ready for questions.
Great. Thank you so much. That was an incredibly valuable insight into, I think, the fundamental issues to be solved around direct air capture, and then zooming out to the scale required. You know, on the face of it, 152,000 square kilometers does not sound insurmountable, so that's promising. So I'd like to introduce Philip at this point to start with the Q&A, and then we'll interleave one-on-one through the Q&A for as long as we can.
Yes, thanks so much, Connor. I encourage the audience to keep sending the questions. We have quite a few in the chat, so I'll just kind of work my way through it based on upvotes. So one question that came up was, what happens with the CO2 after it's captured? So we know from industrial CCS plants that they compress the CO2 and they ship it away, or they put it in a pipeline. But presumably you cannot build a pipeline to every individual direct air capture plant.
So I'll take that one. So we do believe that sequestration will be something you'll have to do with direct air capture. But one of the advantages of direct air capture is that you can potentially position the direct air capture technology directly above the CO2 sequestration site. So if you were to do sequestration on land, you could certainly think about locating the DAC plant either on top of or very close to the place where you wish to sequester it. Now, if you believe that offshore sequestration is going to be the approach, unfortunately, probably building 150,000 square kilometers of direct air capture above the ocean is probably not something we want to do. But you could imagine, again, locating the direct air capture very close to the coast, and then using pipelines to move the CO2 to ocean bed capture locations. So we believe that capture and sequestration will be a valuable part of this, but we also believe that this is the situation where CO2 capture at the scale of maybe a few 100,000 kilotons might be something that we could actually use and convert profitably into other chemicals, for example. So coupling it with renewably produced hydrogen to produce fuels and chemicals is certainly another alternative that is being looked at. Chris, did you have add anything to that?
So it would make sense to kind of cluster the direct air capture plants. You wouldn't just have like an individual device in the landscape somewhere. It would make sense to kind of put them together, I guess, into clusters.
Yeah, I mean, putting them at the level of 1,000, say, tons a year or smaller really implies that you have a use for the CO2. And you find that if you examine the amount we have to capture, we rapidly run out of uses of CO2 at that scale. There's only a certain amount of fizzy drinks you can have, and that really just doesn't scale with the problem of CO2 capture for climate change.
Great. I'd love to hear, so this was a question that came in, but I'm personally curious too. So what role can a technology partner like Microsoft play in direct air capture, and where can technologies like cloud computing, AI, and machine learning help?
So I can step in. I'm the process modeling and simulation person, And so I would say that one of the things that we're definitely going to need to do as we move forward is understand how high performance computing can help us design these systems. One of the unanswered questions at the moment is exactly how arrays of contactors will behave if we set them up. So you can imagine flowing CO2 past an array of contactors and the CO2 will be removed from the air. How quickly does it recover on the far side of the contactors? How do we space the contactors on the landscape? How do specific features of the landscape affect the performance of this? And this will require substantial computing power to be able to work out those kinds of ideas. Also, we want to design more effective contactors. And although we have the models necessary to do that, carrying out the sort of computational fluid dynamics simulations coupled with porous material behaviors is actually quite compute consuming. Did you have anything to add to that, Chris?
Just to re-emphasize that on the sequestration and monitoring side, where Felix is working, is very, very well aligned with the needs and the opportunities in the high-performance computing space.
Okay, yeah, that makes a lot of sense, I think. Then we have another question that says, I'm curious about the amount of air that has to be moved. Could a farm of these DAC systems cause localized weather phenomena? And I guess that's also a question where maybe the simulation aspect can come in again there. You do some kind of forecasting simulation to actually model this, but yeah.
Yes, so the answer is
again.
Yes, well, the answer is we don't know the answer to that question, and it's something that we would like to examine again to de-risk the deployment of direct air capture. I mean, to take a classic example, we really at the moment don't understand how, for example, pollination, all right, when we have trees that in the spring releasing pollen, if these were near direct air capture systems, we don't really understand how the pollen might interact with our direct air capture, changing its performance. One of the things we're looking at the moment is how does air temperature affect the performance of these systems? Do we need different capture materials, different device designs if we were trying to do this, for example, on Antarctica, as opposed to doing it in Florida? So these are all questions that we would like to analyze using modeling and simulation with the limited lab experiments that people like Chris are able to carry out, because, you know, building these systems and then going, oops, that didn't work, is probably not a great idea.
Great. So there's a question on economics as well. I know from reading through some of your papers before this that you've looked in depth at the economics of direct air capture also. So the specific question is, where does the misconception of the $1,000 a ton come from? And then it would be great to hear any commentary you have on the evolving economics with reference to the increasing carbon prices in places like Canada and the EU, and how you see that stacking up as the technology advances and hopefully costs come down.
Why don't you take that one, Chris? Sure.
So with regard to the components of the cost, so the original estimate of, say, $1,000 a ton was achieved by taking a process that was designed and commercialized for high concentrations and applying it to low concentrations of gas. And I think the economic estimate for that type of process was a reasonable estimate. So what the startup companies have done in the interim is to design processes that are specifically targeted to the unique challenge of the low concentration gas that is air. And what that does is it reduces the cost of the contactor, it reduces the cycle time, and it minimizes to the extent possible the amount of energy that's used in that second step, the endothermic desorption step, which is a high operational cost step. And then finally, by having a system that's designed for these ultra dilute mixtures, you can thereby reduce the capital cost by making the cycles be as short as possible, so that you can deploy your equipment and cycle it as quickly as possible. And all of those individual elements go into creating processes that can be, I think today, if you talk to the startup companies, the technologies can be, you know, $400 to $800 a ton, and the idea, by using the learning curve models that exist in other fields, that you can project these costs over a period of 10 or 20 or 30 years, dropping down to the vicinity of $100 a ton or maybe lower. And so what was the second aspect of that question again? It was about
Economics, like with respect to, say, the existing carbon prices in Canada, which I think are around like $60 to $80 a ton, and EU, I think something similar.
All right, so yeah, so the fundamental thing that's different from the previous example that I gave about learning curves and cost reductions with regard to solar is that solar produces a product that everybody on Earth wants to buy. Every single human being on Earth wants to buy energy. And right now, the product of negative emissions of CO2 is not one where markets are well developed. And so for a long time, you saw a stall in the development of these startup companies and these technologies. And I feel like the world shifted seismically around 2018 in the United States with the consideration of negative emissions for credits in the California Low Carbon Fuel Standard, which typically has trading on the order of $100 to $200 per ton. And then 45Q is the federal tax credit at $50 a ton. And then you have carbon markets, whether they be in Canada or parts of Europe, that are also bringing in ways to monetize that carbon. And those things happening quasi-simultaneously really has increased substantially the momentum for new ventures and new companies moving into this space, because there now becomes clearer paths to try to monetize the technology in the early stages when it's still not that efficient, which is critical, getting the technologies down the learning curve to the point where costs are now coming down enough that you can imagine widespread global monetizing of these technologies via hopefully what will be at some point in time global costs on carbon.
Thank you. So there was two questions relating to the location of capture plants, and I'll combine those questions, I guess, into a single one. So the question is, does it make more sense to cluster them, or would you get a similar, I guess, effect if you more spread them out evenly? And are there some geographical regions that lend themselves more to the installation of these capture plants than others?
So I guess I'll jump at that first. I think that taking a bird's eye view, the nice thing about CO2 removal from the air compared to conventional post-combustion capture at point sources is that your feedstock, the air, is in principle the same from a carbon perspective everywhere on Earth. So that means that large installations versus scattered installations, that's a systems optimization. That's the area that Matthew works on, and he can talk about that in a moment, whereby I think any of the solutions in principle are feasible because of the fact that CO2 is the same everywhere. There are, however, there is also the difference in climates in different locations, and that's something that we at Georgia Tech have started to think about trying to exploit. So for example, when you're capturing CO2, if you co-capture a lot of water, that comes with an additional burden to process that water from an energy perspective. And so if you're operating in Louisiana or in Florida, you have to have a process that's suitable to manage that high humidity, which is going to be different from if you're operating in a more arid climate in Arizona or Eastern Washington or something like that. And furthermore, you can imagine also temperature variations, right? So in Florida or Louisiana, the amount of water the air can hold is much higher than in Montana or North Dakota as a consequence of the change in the absolute humidity as a function of temperature. And so we think that the varying climates could lead to a future where we imagine 20 years from now, there might be 5 or 10 different technologies that all take CO2 out of the air, but are specifically optimized for operating in a particular climate regime, where maybe the Florida process wouldn't look very good in Arizona, and the Arizona process might not work in Massachusetts, for example.
Okay, maybe a bit of a follow-up question there too. So one aspect I read about this Climeworks facility that they're building, that they built that in Iceland, if I remember correctly, because they wanted to use some of that passive heat from geothermal energy to do some of that or to use it in the stripping process. So I thought that was very interesting. I guess a lot of people have the question too, if there are other sources of heat or energy where you can kind of take advantage of that. I think some people mentioned, oh, data center generates a lot of heat. I guess it's probably not enough for direct air capture, since you mentioned something 60 to 120 degrees Celsius. I guess the data centers are a little bit below there, but are there other maybe possibilities to take advantage of existing energy sources?
So let me just step in and say that we have actually thought about data center integration. And the answer is that what you can do is you can circulate a organic Rankine fluid through the data center to cool it. And then with a vapor compression cycle, you can actually upgrade that heat into the range necessary to make direct air capture work. So it's a little bit harder, but basically think about a heat pump. You can effectively use a heat pump because the amount of temperature you have to raise the system by is not so much that you can't use something like a heat pump. So a heat pump will be effective in the case of using it, for example, coupled to data centers. So we have actually considered that particular source of heat. But again, you recognize that the amount of heat required here is significant, even for modest scale implementations. And again, do we have the space to build a lot of direct air capture contactors near data centers? That I don't know about, but if it's possible, certainly that source of low-grade heat can be upgraded using heat pumps to make this kind of system work.
Yeah, there's a lot of low-grade heat and manufacturing processes that you can imagine using. But if you're going to do that, you're also, going back to a previous question, envisioning a future where you have a lot of smaller scale installations that are scattered around, because the economics might tell you that using that heat is valuable, but then you've got to transport the CO2 as a product. Or you might model and say that co-locating by the sequestration site and minimizing transportation of CO2 outweighs the advantage of having a little bit of free heat with these distributed type systems. And this is why sort of a systems-wide optimization is needed.
The other approach would be, and this has been discussed, is, you know, now you've captured the CO2 and now maybe you can bring in either a methane or something like that. Basically be able to capture the CO2 coming off the methane in the same way, or do something similar and combine the hydrogen that you're getting there, or make the hydrogen renewably from a fuel cell, from an electrolysis cell, and take that hydrogen and combine it with the CO2 and actually make locally fuels or chemicals. I think that turns out to be very, very energy intensive in compared to just capturing the CO2 itself, but it would allow you to move to an energy system that was much more distributed in terms of its production of liquid fuels that might be useful, ways of cutting down use or removal of fossil fuels from the ground as some intermediate strategy to generate useful products.
Great. Perhaps we could finish with one final question. There are a few questions that have come up in the chat related to portfolio of technologies and standardization, and I'd love to put a Microsoft specific slant on that. You mentioned earlier that Microsoft have some existing relationships with Climeworks, and the wider fact that Microsoft have a carbon negative goal by 2030. So we are out in the market today purchasing carbon removal. And so I'd love to hear any advice that you have from a technology point of view as to how that Microsoft carbon removal team could direct their purchases to have the most positive impact on the technology to drive it forward. And then whether the different offerings, like the major energy companies announcing carbon removal, like for example, ExxonMobil, are they all using the same technologies or are they using different ones?
Why don't you have a go at that one, Chris?
Okay, well, I'll tackle the latter question first, and then have the first question go back to Matthew. So in addition to the startup companies that are in the space, there are a lot of what I'll call conventional energy companies whose core technical expertise within their organization is very well aligned to remove CO2 from dilute mixtures. So if you're talking about a major chemical company, a major oil company, major gas processing company, all of these companies have the expertise in order to work on this topic, but they haven't necessarily deployed that expertise in the past to deal with these ultra dilute type of separations. So what you see them doing now is pivoting, reorganizing, developing alliances to deploy those experts on this ultra dilute challenge. And I know that in some cases, these large energy companies are also, partnering with startup companies and trying to find synergy there as well. So I think there's a lot of activity in this space. They're not all using the same approaches for sure. There's a fairly good variety of different approaches, but there's, I would say, a handful of approaches now that I think are most attractive for near-term and medium-term deployments. And so that's why you see some companies clustering around particular approaches, because they might be perceived to be more quickly deployable. But I think there's also plenty of room for this long-term problem to look for the wild and crazy out there ideas as well. And Matthew, do you want to tell Microsoft how they should invest their negative emissions dollars?
Well, so I'm going to come back to my statement, all of the above. I think it's really important that we support a portfolio of technologies, some of which will be cheaper and nearer term, and some of which will be more expensive and longer term. We do need to start buying direct air capture so that we can start moving down that learning curve. And I would applaud Microsoft for stepping up and buying some of the product from Climeworks at high dollar numbers. I think that's really, really important that we do that. I think the lower cost options are important. My one concern about some of the lower cost options is of course the permanency of the storage. That is one of the things that, along with seismic monitoring, to be able to figure out that it stays in the ground is one of the advantages of doing direct CO2 capture and sequestration is that you do have a pretty good guarantee that it will stay there, whereas enhancing natural systems or growing more trees, one does have the concern that might not persist over geological timescales necessary to really remove the CO2. But I think it's an all of the above, and I applaud the idea of going for a portfolio that supports multiple different approaches at multiple different scales.
Great, thank you. Why don't we hand over to Philip, given the time? Perhaps we could wrap up there.
Yeah, so I want to thank the speakers again. Thanks everybody for attending. This was an amazing talk, super informative. Yeah, and I know we already been over time. I know there's some maybe leftover questions. I may forward those via email. And yeah, thanks again for the speakers. And I think we do have an upcoming RFI lecture series talk. Please join us on November 11 for adversarial models from options pricing to trade execution. And this is a talk that's going to be given by Chaitanya Bandi from the Kellogg School of Management at Northwestern University. So that would be another amazing talk. Please join us for that, and thanks again.